This is, wow, that's a great noise. Okay. Yeah, so a couple things that we just learned is that for some reason the mic does not properly work with the computer, so the recording doesn't go through the computer, so I'm doing it through my laptop again. And hopefully the people online can indeed hear me. And second thing, as you may have seen, there was like a midterm right before us, and that midterm ended up kind of like taking up some of the start of this class time. So that partly answers one of the things about our midterm. So our midterm ends 5 minutes before the end of class. And the reason for that is so that we have like this extra time to gather the midterms. And also we start 5 minutes kind of later because there's a lot of students, so we're gonna have to hand out a bunch of midterms. So that's the reason the midterm is 70 minutes, because of this like, I guess, time interval that we need to hand out and gather midterms. So yeah, why don't I just start saying a few things about the midterm and how class is gonna work. So yeah, midterm is next Tuesday. And as I said, it's 70 minutes. I made a post, so everyone should have got like an email. It was like a Canvas announcement. So the midterm is going to have 20 questions, and you should, it's like the same structure as your assignments. They're multiple choice, there's 20 questions. Some of them have multiple answers, some of them don't, but you don't know which one. So any of the questions can have multiple answers, and you better select all the correct answers if you want full marks. And other than that, you should definitely remember to bring a calculator, because there will be like some calculations. I mean, you can do them basically all in your head, but it would save some time, you know, to do like an integral or a sum or something on a calculator probably. Other than that, I will be going over like a midterm review on this in the second half of today's class. So the way it's going to work is we're going to finish up this like first part of the optimization kind of section that we've been talking about last class. And we're going to see our first algorithm, like an actual algorithm block. I'll write some pseudocode for you guys. It's going to be like a few lines. And then you're actually going to get to implement that on the next coding assignment. So assignment 4 and some other algorithms that we'll discuss after the midterm. And so I'll finish that up for the first like 30 minutes, and then the remaining of class will be going over the midterm review. And someone asks online, are calculators restricted or can we bring any? And the answer is, you better bring a calculator, and therefore they are not restricted. And bring a pencil for the Scantron sheet. If you don't have a pencil, I have an extra. I'll bring extra pencils. Yeah, there's a question. Yeah, you can use a graphing calculator too. I don't really care. It's not gonna, I'm sure it's not gonna help that much. As long as you can add or multiply some numbers, you know, like you're gonna need to, unsurprisingly, maybe like take the integral from like, I don't know, 0 to 10 of a uniform distribution or something like this. Maybe that'll help. Okay. Yeah, and the goal is really not to test your integration skills and stuff like this. Like it's just a necessary kind of step to do some of the calculations, unfortunately. So they shouldn't be too hard. Okay, well, we'll get into the midterm stuff soon. All right, so shall we complete what we were doing before? And that is defining how we optimize over a set of functions, right? So like, where were we? We were at this stage where like we had this, okay, maybe I just take a quick step back. So we defined like supervised learning, and I'm going to jump to this like for the 10th time at this point. But we have this kind of algorithm that's like sort of the like canonical algorithm of a lot of machine learning stuff, which is called empirical risk minimization. And all you have to do is just like minimize your risk, your expected loss. We just have to estimate that somehow. And once you have that estimate, we need to optimize. And so today's discussion is continuing on this. How do we optimize? How do we find the minimum of this number or this function over functions itself? So how do we minimize over functions? And last class, we had this fun little journey about learning about how optimization kind of works. And roughly the story was, it's like you learned in calculus, in the sense that the things we'll care about in this class are going to be where you have continuous functions and you can take derivatives. And if you can take derivatives, the first thing you learned in calculus that you would want to do if you want to find the minimum or the maximum of a function is you take the derivative and set it to 0. And that's roughly the story we discovered last time, which is, in general, if you have multiple dimensions, and you want to find W star, which is the parameter or the argument to this function that minimizes it, well, all you will do is take the partial derivatives in every single dimension or index and set it to 0. That's denoted by the partial derivative with respect to j. You do it for all dimensions j. This will give you W star. Well, in particular, this, like setting this to 0 will give you each one of the corresponding W star j's, and then you put it together into this vector. And this quantity, when you put it together in like into a vector, it's called the gradient as well. So we saw that earlier. Okay. So that's the story. But the thing we noticed is like when we minimize in calculus and stuff, we have like a function, and then the argument to the function is usually like something like a number that's in RD or something like this, or like a vector in RD. And in machine learning, we seem to be tasked with this situation where we want to minimize the estimate of our loss or the empirical risk. This is the empirical risk. But we need to find the argmin over functions. And if we wanted to use the tools we saw above about minimization, there was kind of two things we needed, which was we needed to somehow make this domain something that we know how to minimize over, which is like RD, right? The d-dimensional vector space. So somehow we're going to want to transform that. And we also are going to want the function that we're minimizing over to be convex. And if we have that, then we just basically like directly apply everything we've seen before. Okay. And so how does this work? Well, the way this works is it's you as the designer of the algorithm, your ERM, are going to, massage the kind of what you're doing to fit with your mathematical skills that you know how to use before. And so there's a few things we get to pick, right? One of them being the function class. Unsurprisingly, we're going to pick it, to make it such that we're optimizing over like a domain like RD. And then this empirical risk, well, it's a function of your function class will change this. Also, the loss you pick, the little L guy, will also change what this function is, right? So if you look at this thing changes depending on L. And so it turns out that we're going to also pick L and this function class in such a way that this whole thing will be convex. And the story looked like this. We said, well, wouldn't it be great if every single function in the function class could have this like one-to-one association with a vector in RD? Okay. If we had that, then it would be the search over functions would be the same as searching over parameters in RD. And we go ahead and do that. And the simplest choice for a function like this that you might be familiar with are linear functions. And these are functions of the form feature, that's the input to your function, times some number, or sorry, by times I mean dot producted with some number. Okay, so you have like an input, and then you take the dot product with just some vector here. This is called a linear function. And in one dimension, as we had seen, this looks like a line where the W is just the slope of the line. Okay, I'm going to point out something that we will fix in a moment, which is that lines usually have an intercept, like plus b. We're going to add that in a moment. But for now, just to finish the story of where we had before, so far we have lines, and the W defines the slope. And if you have 2 dimensions, then you get not quite a line, you get a plane. And then in 3 dimensions, you get like a hyperplane kind of thing. Okay. And so now our function class is going to be the set of all functions that map from features to labels. And in this case, we're studying regression. This is important. So from now on, we're going to focus on regression, just to pick one of the settings. And there, our labels will just always be the real numbers. And later on, we'll study classification. And that'll be like 3 or 4 lectures, or 3 or 4 weeks from now, actually. So we're going to just kind of nail down this regression setting, learn a lot about that. And we'll come back to classification later. Okay, and so yeah, we have all these predictors, models, and they have this property that they all look like these linear functions. And so now there's like this one-to-one correspondence. Every function in our function class is associated with a corresponding, we're going to call, this is called a parameter or a weight vector associated with each function. So there's this one-to-one mapping. And so we saw that if we wanted to minimize this function over over the set of all functions in this function class, well, first of all, we can just write out what is the definition of this. And that just means plug this in. Plug in the empirical risk. And if you look at this object, you're like, okay, I know this function class. I've chosen it. So I know that the functions I'm minimizing over all have this type of form. And the only thing that differs is the W. And so the above minimization is equivalent to this, which is plugging in this function, since every function in the function class has this form. And then the only thing that differs between functions is their weight vectors. And so really all you have to search over is weight vectors. And so that's why we're minimizing. We've switched the minimization over functions to weight vectors of this object here. Okay. Now, at the end of the day, we need to produce a predictor, right? This thing gives us the minimum value, but we want to find the actual minimizer, which is like the argument thing. And the way this works is we need to somehow output a predictor f hat. That f hat is going to come from our function class. What that means is f hat will look like this. It will be input dot producted with a parameter. And the question is, what is the parameter? Well, the parameter is going to be the parameter that minimizes that above quantity there. Okay. So there's this little bit of a step, which is like you find the argmin parameter or the minimizer of the empirical risk. And then you plug that in to this dot product equation, which will give you f hat. And that is really your learner. And okay. And at this point, we're like what's left to do? What's left to do is solve this problem. We saw how to do this. We're going to take the derivative in every single dimension of every one of these d dimensions, and we're going to set them to 0 and solve for what w hat is going to be. And for us to know that that is the true minimizer, there is another property we needed, which is that the object we're minimizing over, and by object I mean the function, let's call this g of w, right? We need it to be convex. And in last class, I said that indeed, if we pick the loss to be the squared loss, and this is like a choice for a reason in some way, if we pick it to be the squared loss, then indeed this function of the parameter w, right? It is just a function of w. Well, that is indeed convex. So that's the answer, yes. Okay. So at this point, all that's left is just math. And really, this could have just been asked in your calculus course, which is like, you have this function, and now please find the minimizer, or they would maybe say yeah, find the minimizer, which is take the derivative, take every partial derivative, set it to 0, and solve that system of equations. And that is all we're going to do for the rest of the class for 20, 30 minutes. And then we'll move on to the midterm review. But before doing the math, is there any questions about this whole setup? Because this is super important. Oh, there's one thing that actually I'm going to have to discuss, this plus bias term. We're going to fix that in a second. But before I do that, is there any questions about this idea of choosing a function class that can be described, every function being described by some parameter? Because this is really going to be the story of all of machine learning. And I mean, maybe to I don't know, foreshadow some things in the future. For neural networks, your neural networks are going to be a function class, which is the set of all neural networks. If you know anything about neural networks, there's a bunch of neurons, and they have different weights in how they're connected. And then those weights are you can describe it as a giant vector, which is of length number of weights. And then you have a function class that is just literally described by no longer a linear function. It's going to be some more complicated thing, but it's just a giant long vector that corresponds to each function. And guess how minimizing a neural network works? It's the same story. You need to solve this argmin problem over the parameters that describe every neural network. And so this step is extremely important and done all the time. Okay. So if there's no questions, we need to do one slight fix, which is we could do everything and everything would be okay, but you might notice that it's we could just improve this function class just a little bit, in the sense that imagine the true function that actually represents your house prices or something looks like this. there's a slight problem. We can't model this line. Like even if we were in 1D, imagine you just had one feature, d was equal to 1. You can't even represent this line using a function class. And the reason why is because it has a y-intercept that's non-zero. So let's call this y-intercept b. Okay. Well, it has a y-intercept that's not, okay. Yeah. Well, we'll call it, instead of b, I'm going to just use w0, just to match our notation in a second here. And so we need to somehow model this. And let's say this is the line that has, I don't know, slope 1/2 plus w naught. Okay, so this is like a familiar equation of a line you've seen. This is like the slope, and this is the y-intercept. So naturally, we're going to want to add a y-intercept to our function class. So we're going to want not just the linear functions, but we're going to want the linear functions that can be shifted up and down. Right? So in one dimension, you can see what that means. That means you could take a line and you can move it up and down. This is sometimes referred to as the bias. Okay, so you might hear in machine learning world, there's weights and biases. The biases are this corresponding shift of your function up and down. And so if you have 2 dimensions, then it just shifts your plane up and down and so on. It should be very intuitive that you want to be able to shift it up and down for the case where your feature is 0. Okay. And the way we're going to introduce this is we're going to want to add like a plus w naught term. That's another parameter. However, it's going to be really ugly to carry around this bias, and some people do it. Like some other courses and other literature will have like a separate weight and a separate bias. But maybe the more common convention and what we're going to use is we're just going to say, okay, from now on, okay, let me just write something down first. So if we want to introduce a bias, maybe I'll do it here. It's going to be like a little side note. So if we wanted a function of a vector that looked like x dot producted with w plus some bias term, which I'll call w naught for a very good reason that you'll see in a moment. If we expand this out, what does this look like? This looks like, you know, x1, that's the first index, right? Times w1 plus up to xd, there's d dimensions, times wd plus w naught, right? This is like the definition of the dot product. Now you might notice, well, what's going on with w naught here? Well, w naught, I can write it as like the number 1 times w naught, of course. And now I can just rearrange the equation a little bit to make it a little bit prettier. So I'm going to move all the terms to the right. I'm going to take this guy, put it in the front. This is obviously the same equation, right? I've just moved it to the left, and then I add the dot product to the right. And now you might look at this and be like, oh, this looks like a dot product again, but in d+1 dimensions. And in particular, it looks kind of like the dot product of the vector that looks like the number 1, comma, x1 up to xd, dot producted with the vector w naught. Of course, there's w1, wd. And that's this is column vector, this is row vector. So these are equal. Okay. And now you can just say like, okay, this looks like, since the first index of your feature has to be, we fixed it to 1, it looks like if you had a feature where x0 was just always fixed to 1. Okay? Okay, and so now this is what's going to happen. So from now on, whenever we have features and so on, we're always going to refer to the features as the original feature appended with a 1 in the very beginning. Okay? And so everywhere from now on, we're not going to talk about d dimensions. We're going to talk about d+1 dimensions. And the 1 is going to be this +1, or this 1 in the 0th index. And that is going to allow us to have this bias term, which will be important to have like a shift in your functions. And this will come up everywhere. Even if you like more generally, imagine we didn't have just lines. We had, let's say, like polynomial functions. Well, it would be very sad if our polynomial function always had to be, you know, its minimum had to be at the at y equals 0. You would like to be able to shift these things. And more complicated functions, you'd like to be able to like shift them to be like up here and stuff like this. Okay, so the way this is going to work is we're going to go back, and from now on, we're going to say our features are d plus 1 dimensional. And our function class is going to map d plus 1 dimensional features to R. And our linear function class is going to be the set of functions of d plus 1 dimensional features. And here, this parameter w, this weight vector, is now d plus 1, because it has this extra w naught. And this is d plus 1, and this is d plus 1. And from now on, it's always going to be d plus 1, because you're going to have the weight vector plus the bias term, which gives you d plus 1 parameters. Okay. So that's going to be the story from now on. Is there any questions about that extra addition of one extra parameter? Okay. So yeah, the rest of the class will solve for w hat. So that's our goal. So solve for w vector hat. That's what we're going to do. And so, yeah, kind of for the sake of time and not to bore you too much with the details, all the steps are in the course notes, like the PDF version of the course notes. So I guess I'll skip some like obvious chain rule steps and so on. And yeah. And so we can get to the midterm review stuff. And then you can review that after, but it's like you'll see the main idea. So what do we need to do? We need to take the partial derivatives of the following function, which is L hat of w vector. So we need to take the partial derivatives of this, set them to 0, and solve the system of equations. And that's what we're going to do. And let me just remind you, this function, we've given it, it's a new definition, right, which is before we knew what L hat of f was, that was the empirical risk. And that definition was the following. And then we said that, okay, when we're dealing with linear functions, since f looks like this, we're going to denote this object here. I guess it's done below. We're going to denote this object here as L hat of w. And so when you plug in a vector into L hat, that means this equation. And when you plug in a function, it means this equation. That should, like, based on the argument, you should be able to parse what the corresponding function does. And yeah, this is clearly an abuse of mathematical notation, but you should get comfortable with it because, as you have noticed with random variables and other places, this gets done all over the place in math to make kind of things look cleaner, but you have to remember how to decode it. Okay. So given all that, let's do this partial derivative stuff. So first of all, what is this object? Well, it's the kind of sample mean of n loss values. So you have each one of these xi vectors. You take its transpose with the w vector, and you compare it to yi, and you square it. So this is what the object is. It's you have n samples of how your predictor does on the squared loss. All right, so let's take this derivative and set it to 0. So first thing that we're going to do is maybe you can do this all sorts of ways. You could really kind of almost do it directly. But let's just do one step to make this a little more clear how what's going on. So let's just expand the sum, right? So let's expand the sum. What is that going to look like? Well, you know, when I equals 1, you have x1 transpose w minus y1. And then plus, and then you do this n times, right? That's what the sum is. Okay. So if you remember, when you take a derivative, the derivative of a sum of objects, you can take the derivative of each individual thing, right? So for that reason, I'm going to give each one of these kind of terms inside the sum a name. I'm going to call it like kind of the loss for that data point. And the natural name is L hat index I of w is going to be equal to like xi transpose w minus y. And since each one of these terms in here looks the same, if we just take the partial derivative of one of these li's, we're going to see it's the same pattern for all the others. Okay, so that's what this object looks like. And maybe just to really make things. Oh, there's some things that are missing, right? We kind of completely forgot to square this object. And this thing is obviously this thing squared. And what I wanted to say is like we're going to need to take the partial derivatives of W vector, right, for each of its corresponding dimensions or indices. And right now it's kind of cryptic what the dimensions are doing. So let's just take one more step to write this out a little bit more explicitly, and then we'll see what's going on. So this dot product, as we have seen, looks like this. It's like the xi vector, and then you take its first index and you multiply it with W vector's first index, and then you do this d times, right? Oh, and here, remember, since we have d plus 1 dimensions, we will start at index 0. And you go xi index d. This is no longer a vector. W, oh, what's going on there? W0 and WD. And then you subtract from that yi. And you square it up. Okay, so why am I writing this? I'm just writing this to make it very explicit. Where is the corresponding indices of the W vector coming up, and how are these partial derivatives going to look like? So let's just decode what happened. This whole objective is just basically a scalar, like 1 over n, times a sum of n terms. Each one of these n terms looks like this. And we're going to need to take the partial derivative of each one of the dimensions of W. So we're going to take the partial derivative with respect to W0, W1, up to WD. And you can see what that's going to look like is we're going to have to take basically the partial derivative of this function. And you can see it's not that hard. Like you do the chain rule. I'm not going to do all the steps. There's 2 steps of this chain rule, but you're going to take this square, take it outside. You're going to get left with this term, and then you're going to take the derivative of the inside for the corresponding Wi. So let's write that down. Okay. So, and I guess the way I wrote this is, so this is going to be kind of like new notation we defined. And so this above quantity over here with this new notation, I can just replace all these terms with these LIs, right? So this is like L1 hat W. And then this guy is Ln hat. Okay. Maybe this is like way too verbose for you people, but better to go through these steps once, because then later on we'll make more jumps into how this works. All right, so all I've done is rewritten the original function at this point, right? Now let's do this partial derivative, actually. So this is our goal. We want the partial derivative of the original function, L hat, with respect to a particular dimension, Wj. And we're going to want this for all j's, j equal to 0 up to d, right? We're going to do it for a single j, and we're going to see that by symmetry, it's actually going to be the same for all the j's. Okay, so that's the partial derivative we want. And what does that look like? Well, that looks like the partial derivative of this thing. And as I said, derivatives have this linearity property, which means that the partial derivative of this object, which is just L hat, is equal to so scalars, you can take them outside of a partial derivative, and then you take the partial derivative of each object within the sum. So this is equal to 1 over n times the partial derivative of L1 Wj plus up to partial derivative of Ln hat with respect to Wj. Okay. So hopefully you follow. And then all that's left is just to, calculate this thing. So let's do that. So we're going to do it for a L hat, and we're going to do it for a particular I, right? So of Wj. And I can just put here j, right? So I, as we saw, I can take values between 1 to n. I will not write that, but j here will take values. J can be any number between 0 to d, right? Okay. So we're doing it for an arbitrary data point I at an arbitrary index j. And by symmetry, it's going to turn out that they're all the same. We just change I in, for all the indices. Okay, let's do this calculation. Yeah, so we're actually just going to do this like visually. I mean, this is just the chain rule. So let's look at this object, right? What's the partial derivative of this object with respect to wj? Well, somewhere in here, and I guess I can write it, there is a wj, right? So at some point in here, you end up with xij, wj, and then you keep going until the dth one, and then you're at yi. So if you want to take the partial derivative with respect to wj, what you have to do is you have to notice this is a function that's squared. So first you apply the first step of the chain rule, which is the derivative of a squared function is 2. You take the 2 out here, and it will be 2 times this function. Okay, what is that function? That's this thing. So let's write that out first. So we're going to have 2 times xi, right? I matching this I vector, dot producted with w, still the w vector, yi. So that was the first part of the chain rule. That is that you take the squared out here and you multiply it by the inside function. And now the second step of the chain rule is you take the derivative of the inside with respect to wj. And so the derivative of this with respect to wj, well, that's 0, because you hold all the other w's constant. This is still 0. All the other ones are 0. And if you go to here, the derivative of this with respect to wj is going to be xij. And the derivative with respect to this, which is also just a constant, is 0. So it's super easy. It's just xij. And that's what we get. We get xij. That's it. And guess what we're going to do? We're just going to plug it back into the above equation, and we have our answer. Okay. So continuing with the above. So hopefully this doesn't throw things off. Like this blue is just some internal calculation. The black means continuing with the above expression, right? So maybe I write that. And it was the same with this guy. Just continuing. Okay. So let's plug that in. And what we get is you take this object, and notice that all of these terms are going to have a 2 in front. So I'm just going to take that out and put it here. And I'll maybe try to make it clear this is a 2. This is not the partial derivative. 2 over n. And now let's just plug in each one of these partial derivatives now. So we're going to need some more room. So first partial derivative, we just calculated above. Okay, so for L1, we're going to need the partial derivative with respect to wj. And we know that that is equal to, and I'll choose to write this xij in front because it'll be nicer for later, I think. So there's xij. What's I? I is 1, right? And then you multiply that by x1 vector transpose with w vector minus y1. And so that's the partial derivative of the first data point. And you do the same story up to the nth data point, and you get x nj xj dot producted with w minus yi. Okay. So that is the partial derivative with respect to a single kind of dimension of the w vector. Maybe some things to note. Notice that here the partial derivatives, if I want it to be explicit, and here again we kind of abuse notation, but remember that this is indeed a function. And it is a function of, in this case, really the whole w vector. And so yeah, like you may have remembered, we sometimes abuse notation. We don't write this parameter in here. But really it is a function of the w vector. And here, notice how it really does depend on the whole w vector. Okay, that's just some quick notes. And so yeah, this is our partial derivative. And that's only for a particular index. And if we change j, we would get a different j here. Okay, so what do we end up with after all this? What we end up with all this is that at the end of the day, we're going to want to set this to 0, right? And we're going to want to do that for all j. And we're going to want to solve. So we have a system of d+1 equations in d+1 unknown values, which is w0 up to wd. So we have to solve that system of equations. And yeah, the way that's going to look is as follows. Oh, I guess there is a slight, okay, so just to clean up some notation, because otherwise it's going to be really ugly to write. Notice that this above object, using our, the summation notation, we can clean it up by just writing that this is 2 over n times, notice how we expanded the sum earlier, now we're going to put it back into a sum. So this is a sum over I equal to 1 till I equal to, whoa, this is clearly n, and this is clearly n. Okay, so we get the sum from I equal to 1 to n of xij, xi transpose w minus y. And this is 1. Oh my goodness. Okay. There we go. So that's what the partial derivative looks like. It's cleaned up this way. Okay. And so we want to set that to 0 for all j. So let's kind of solve this equation, or like, we're going to just rearrange this a little bit. So this is the equation we have, right? It's this equal to 0. So let's just play around with that a little bit to get something nicer. So this object really is the same thing, right, as 2 over n times sum I equal 1 to n of xij, xi transpose w vector, plus or minus 2 over n sum I equal 1 to n xij yi. Right? And we want to set this equal to 0. So if we set it equal to 0, this will imply, this arrow means implies, that we can bring this right-hand side, this thing to the right-hand side. The minus becomes a plus. This 2 over n is going to cancel with 2 over n. And we get the following expression, which is that the sum I equal 1 to n of xij, xi transpose w, is equal to the sum I equal 1 to n of xi j yi. Okay, and that's for a particular j. And so as I said, we have the system of equations, and the system of equation is going to look like this if we were to write it explicitly. You take this for every single dimension of your parameter vector j. So you'd do this for j equal to 0, and j shows up here. So that's one equation. And then you know this also needs to hold for j equal to 1 and 2 up to d. And so you get this system of equations that looks like this. D and D. Okay, and just to be clear, this is for the case where j equals to 0. This is for the case where j equal to d, and then everything in between. Okay, so hopefully this still makes sense. All we've done is we've taken the partial derivative of our empirical risk with respect to every dimension. There's d plus 1 dimensions. We've set them to 0. And then what do you have? You have d plus 1 equations. And that's all I've written. I've written the d plus 1 equations for you. And you can go back and double check the math if you want and so on, but that's what you get. And then it turns out that, yes, you can go and, plug these in and rearrange these equations and so on, and that can take a lot of time. But if you took linear algebra before, it turns out that if you have a system of equations, you can put it one side into a matrix, the other side into your targets, and then you solve for the vector multiplying the matrix very, very easily. And so that's all we're going to do. So roughly speaking, we're going to look at this object here, and we're going to notice that each one of these is just a number times a vector as a row vector summed up. And the sum of row vectors is still row vector. And you have d of them. So this object is going to be a matrix that has n rows, or sorry, d rows, d plus 1 rows. And it's going to also be d plus 1 dimensional this way. So it's going to be d plus 1 by d plus 1 matrix. This is a vector, right? That's being the dot product with that. with each one of these guys. If you remember the so we can call this thing, we're going to call this thing a matrix A. And you might notice that this matrix A, described in the way above, if you take matrix multiply with the W vector, you get exactly this thing. These are the corresponding rows of the matrix. And you might remember one way to think about matrix multiplication is if you have a vector, you take that vector and you multiply each row of the matrix. And then you get the corresponding vector after. This thing on the right, well, this is just a number, right? This is a number, this is a number. You sum up a number n times, you get a number. You can stack them all vertically, and you will get that this guy over here is going to be what is called the B vector, commonly in. And this is a very common equation in linear algebra. A times some unknown, this is your unknown, is equal to some vector that is known. Okay. And this has, in linear algebra, this is like, yeah, set of linear equations, and it has a solution, which is if you take the left-hand side and you multiply it by, maybe I'll write, you multiply by the inverse. Okay. Like roughly speaking, if these were numbers, what would you want to do? Right? You want to solve for W. What would you do? You would be like, oh, I want to divide the left-hand side by A so that I have 1 times W. And then on the right-hand side, I get this. But since you have matrices, you can't divide matrices. So the parallel or the kind of equivalent step in matrices is called the inverse, right? And so you're not going to need to know how to calculate the inverse. You're just going to call it on the computer. There's literally like, if you have a matrix, you in NumPy for Python, you just do like dot inverse or something like this. But all you need to know is it's the thing that's like the division. And if you apply the inverse on the left, this object will become just the identity matrix. And the identity times W will just give you W. And on the right-hand side, you get A inverse times B. Okay. And yeah, so you get W hat equals to A inverse times B. And if you define this matrix on your computer, and you define this vector as well, and then you apply the inverse and do the corresponding matrix multiply, you will get the corresponding W. And this W is W hat, which is the solution we were looking for, right? So this W is the solution to our system of equations, which we got by taking the partial derivatives and setting them all to 0. Okay, and it turns out that this A guy has a, so you can write these out in just like a slightly maybe nicer way. So B, yeah, we saw what B was. B is this like above thing here. And you can write out like slightly nicer, this B thing. So, okay, let's define these things. So you saw like visually what B is, and you saw visually what A is. But you can write them like more mathematically, and you have to use this actually when you program, which is first B, the B vector. You can stack all the x's as a vector. That's just the x vector. And then you can multiply by y. So it's the same as taking the sum I equal 1 to n of the x I vector times yi. And you can just confirm that this is indeed the same thing that we saw above. And the A thing, well, you can do the same thing. You take this guy and you stack them vertically. That's just the xi vector. This is xi transpose. So it turns out that you can also write this as I equal to 1 of n of xi stacked, like all those entries stacked vertically, that's just the xi vector, times xi transpose. And this object also has a name. It's called the outer product, but you don't really need to know it, the name, but you can know it if you want. And yeah, so on a computer, this is really what you implement. Okay. So all this being said, let's conclude with an actual like algorithm block, and then we'll get to this midterm review. So we have our first algorithm. Like we can actually take some data and output a function at the end. So we have a learner that can take in data, output like an actual predictor, a model at the end that can then predict things. And it's coming from this like principled way, which is it's minimizing the empirical risk. Okay. And this algorithm is really just like the closed form solution. So this kind of equation is called like a closed form solution, right? This is like a closed form, we'll call it the closed form linear regression learner. So here's some names. If you took statistics before, you may have noticed this is the regression setting. It's called the linear regression setting because our function class is a set of linear functions. And we have this closed form solution for this linear regression setting. And so we'll call this like the closed form linear regression learner. We'll see later on, we're not going to have such nice closed form solutions. Okay, so we have this algorithm. And now I write some pseudocode, which is only a couple lines, right? So how does this work? Your algorithm takes as input some data set, right? It looks like this. It looks like x1, y1, right? And like when you're programming this in Python, I guess you put this thing in like, well, it's going to be in like a NumPy array or something, but before you use NumPy, this would be like a list, giant list of your things. And a list is, if I recall, an ordered thing just like a tuple. Okay, so you have this input. Then what do? Your algorithm is the following, which is your learner. It's going to compute A. And so A is going to be set as we saw above. You're just going to compute it. You can implement this in a for loop. In the assignment, you'll see that doing something called vectorizing this makes it more efficient, but a for loop does the trick as well. And the for loop will just implement this sum, right? Which is this xi vector times xi transpose. So you take a for loop and you apply this like outer product operation. Now you get a new variable A, you get another variable B by setting it equal to this sum I equal 1 to n of xi, yi. And then you do another operation, which is you calculate your w hat vector, which is the thing you're trying to solve for, as A inverse. So you'd call like literally A dot inverse or something in NumPy. And then you do a matrix multiply, or yeah, with the vector B. And that produces a vector, which is the solution. And remember, our learner needs to output a function. And so it will return the corresponding function, which you can like define the function in line as like, I guess, a lambda function or something, but or you do it outside. Anyway, however you want to do this in your code, you're going to output f hat, which is a function of x, as x transpose w hat. And that is your algorithm. So this is our first algorithm. And this actually works quite well on problems that really you can actually fit with a line. And yeah, so this actually does work fine. And this is just, you may have heard this is just like linear regression. We're going to get into more complicated things later. And so some caveats are things like taking this inverse, this A inverse thing, can be computationally expensive. So we're going to want to avoid that. And we're going to talk about that next class. And also sometimes the inverse doesn't even exist. But that's OK, because you can just use the pseudo inverse, which you will in your code anyways. OK, so that's a learner. And it's really this simple. Is there any questions before we jump to this midterm review? OK. Well, let's do that. OK, how is this going to go? So this is just going to go, I'm going to kind of go over all the stuff that we sort of went over, but just like maybe the most important parts. And then try to also mention, since I've already made the midterm, I'll try to remember what I did and somehow point out some useful things that you should actually know. OK, there's going to be a little bit about this like math notation. There may be, I think there's like one question or something on the actual notation, but obviously future questions, if you don't know what like an element of symbol means in subset, you're probably going to be in trouble because you might be asked like, I don't know, is this function class a subset of this function class? Well, you should probably know what subset means. So all of it kind of builds on this notation, right? But anyway, you should know like these set notations and the set builder stuff, as you've seen a lot. There is this, we define functions as like, you know, a function satisfies this, and then it can have other properties like it also looks like a linear function or maybe polynomials. And hopefully, you know, you can see how the story's going. You know, in the assignments, we've defined like the set of all polynomials up to some degree. Unsurprisingly, later on, we're going to study the set of functions that is not just lines, but polynomials. And those will be able to fit your data better and stuff like this. Okay. A very important thing is this Cartesian product, right? It's denoted by a set with an x, another set. Okay, this is the way it has. This is like the arguments are set and set. And what does it produce? It produces another set of ordered objects. And here it would be ordered pairs. If there was 3 things Cartesian product, it would be an ordered triples, and so on. And these are called tuples. That's important. Okay. Dot product we've been using a lot today's lecture, but we write it as x, or like your vector transpose, which makes it into a row vector. So visually it looks like this, times the column vector, which is a row vector transpose. So, okay. And this is the equation for it. I don't think I put this on the formula sheet, but you should know that the dot product, I expect you to know, is, you know, the multiplication of each index. Okay. And then you should be able to understand like how to parse like functions. In particular, this one will be important, right? The learner function, which is like it'll take in data sets of size n. So this is the set of all data sets of size n that contain a single feature and a single label. To be able to like understand that in English as well. Maybe you need to like, you can be asked that or something like that. And then this outputs a function. So the codomain is the set of functions. Okay. And like, yeah, maybe it's not that important. Okay. So that's your learner stuff. Okay, let me just say a few more things about this because I guess it's sort of important. So you like if you have a learner, for it to be a valid learner or a valid definition of a learner, first of all, the object it takes in better actually be a data set of this form. So if you set n equal to 2, you expect elements of this thing with n equal to 2. And what do they look like? Well, you should be able to parse this. You should be like, oh, the things inside are going to look like pairs, ordered pairs. And then I need to take the Cartesian product of those things 2 times. So they're going to look like this. So this is like a valid input. If you see, if for instance, this was just, you just got this as your input, true A, it was just like 1, 2. This is not like, this is not valid. The data set is not the right object. You only got 1 data point instead of 2. Okay. And the other thing you should understand is you output a function that maps from, well, whatever is defined here. And here it's going to map from features to labels, 1-dimensional features to 1-dimensional labels. And so any function that satisfies that property for this function class will be fine. So let's look on the right. For instance, you can have anything. It's like this function on the right can be like the number 4 minus 2 times x plus 2 plus 1. And it so happens that these are numbers that you saw on the right, but something like this is also totally valid. Like this could be 20. Take anything you want. It can depend on the data, or it doesn't necessarily need to even depend on the data. That's still valid. You could have a learner that just outputs the function that always outputs 1. It just completely disregarded all the data. It's still fine. You're probably not going to want it, but you should understand that these are all fine. And like, yeah. And then, okay, you just need to understand summation notation. As you saw, it comes up a lot. And there's this interchanging thing when you have like a set that is, or like if you have a tuple, if x is like this ordered set with duplicates, which is a tuple, then you can write summations as the sum of x in this tuple, or you can write it by indexing the actual indices, right? So like I equal 1 to 3. This will be important because it's going to be used throughout as well. So you should understand these are all the same thing. And with functions, it's the same story. You just plug in the corresponding values of x inside the function. So these are all the same thing. As you see, this is all kind of important even for today's class. And then integration, the only thing you need to know about integration is this, like, I mean, this identity is in your formula sheet. I'm not really going to go over it. Just know how to integrate like simple polynomials like squared or cubed or something like that. Okay, that's it. Another thing to know, okay, this is sort of important. I don't know how much, you saw this in your assignments, but you saw when you have like a multivariate random variable and stuff, when you take expectations, or for instance, yeah, even in our like expected loss, that's expected value over a multivariate random variable, right? And that thing, when you write it out explicitly, can have like an integral and a sum, or a sum and an integral, depending on what these random variables are. And so you should be familiar with how to, for instance, calculate the following. So if you see something like this, you should understand that first you take the sum of the inside function, holding y constant. So then you'll end up, so here's an example. So you'll sum up the inside function. So you get like the following. So all I've done is I've plugged in these things. And then afterwards, you then do the integral. So it's like this two-step process. So yeah, be familiar, because unsurprisingly, there's probably going to be at least one calculation of like some multivariate expected values thing. Okay, partial derivatives, as we've seen, are important, and you'll probably have to take one or two of like some sort of easy functions. But yeah, it's if it's single dimensional thing, you write d of f, you take the derivative. The derivative rules are on your formula sheet. And if there's multiple dimensions, then you have to take the derivative in terms of each dimension. So you do it for x1 and x2. Oh, and then the gradient. So there's like the gradient of f is equal to the partial derivative of f with respect to x1 and f with respect to x2, because there's only two variables. Yeah. And so yeah, look at the formula sheet. You see all these like common properties. Okay, then there's probability stuff. So just high level, there's like a few, I guess there's a few high level things that are very important to know. Is that there's these things called outcomes, which is just a set of objects. Any element of this set of objects called the outcome space is called an outcome. And then an event is any subset of it. So for instance, X itself, so it's any subset or equal to, right? And so like, for instance, X, I'll write it in green. So X, well, X is a subset of X. Like the outcome space is itself a subset of itself, it turns out. And so this is an event as well. This is, I guess, an important one. And like, it should make complete sense. What is this event? This is the event that you get some outcome. And that's going to have probability 1. Okay. So this is an event as well. Any other subset is an event for the purposes of this course. Oh, that was interesting. All right, so probability distribution. So the reason we cared about these things is we want to talk about the probabilities of these events. And the way that works is you have a function that takes in an event and tells you the probability of that event. That's it. That's this probability distribution. That's all you need to know. And a random variable is some element of this outcome space that you can also talk about its probabilities. Okay, and then there's all sorts of different ways you can do this. So you'll say like, well, what's the probability that my random variable is an element of an event? And this is the same, it's like the definition will be, it's the same as the probability of that event. And there's all sorts of other common notations. So when you write like, what's the probability that the random variable equals some value x, we really mean what's the probability that x is an element of the set x, which we saw above is just the probability of the event x. Anyway, so you're going to need to know how to parse some of these notations. But some more interesting things is there's two types of random variables you need to be familiar with, which is there's discrete and there's continuous ones. And you can be asked like, is this random variable discrete or is this random variable continuous? And really the defining thing for most of the things in this course is it's going to be discrete if its outcome space is like finite or it's countable, like the natural numbers. And it's going to be continuous if it's uncountable. So if like the outcome space is all the real numbers, then it's continuous random variable. And what's going to happen for these continuous random variables is the probability of any particular outcome is going to be 0. Okay? And so that's when we get into calculating probabilities. So like the reason we define these things, like give these different names, is because to calculate their probabilities, we do a different operation, I guess. Right? So at the end of the day, we want to talk about what's the probability of events. Well, there's a lot of events, and we saw that luckily, to talk about probabilities of events, it's going to be kind of sufficient to just talk about the probabilities of the events that are just contained with single outcomes. They're like these singleton events. And so that's the case for the discrete random variables. And the way that works is like if you ever need to calculate the probability of an event of a discrete random variable, you go and you find your PMF, and then you will say, okay, if I need the probability of some event like this, I go and take my PMF, and I just sum up over all the outcomes in my event, and I get the probability of it. And we've seen this a lot of times. So like the probability of getting like a 1, 2, or 3 on a dice, you can just calculate it as the sum of getting, or the sum of the probability of getting 1 plus the probability of getting a 2 plus probability of getting a 3. And that's if it's discrete. If it's continuous, well, there's a bit of a problem because the probability of any outcome is 0. And so there we talked about the case where you have to use densities, and then you integrate the densities. So the main takeaway is if you have a discrete random variable and you're asked to get the probability of something, you go find the PMF. Maybe you're told that it's like some special distribution, like a uniform discrete random variable. Well, then you go in your formula sheet, you look up the PMF, and you just calculate it in this way. And if it's continuous, then you integrate. And so this is where the integration is going to come up. Okay. And so there's a bunch of common discrete and continuous distributions, such as like the Bernoulli, and for continuous, there's like the normal and the Laplace. And those are on your formula sheet. And if you're told you have a random variable that follows like a normal distribution, you go look it up in your formula sheet, and you're like, oh, it has this PDF. And in your formula sheet, it even tells you like the expected value and the variance of it and stuff like this, I'm pretty sure. So yeah. So those are all in your formula sheet. So get familiar with that. And then we talked about these multivariate random variables. And for that, kind of the story is similar. So if you wanted like the probability of the joint, what do? You need to find the corresponding joint PMF or PDF. If it's this mixed thing, then you use the corresponding chain rule, which I have still written here as the product rule, but this year I've been calling it the chain rule. And then you decompose your corresponding thing into these two things, and you do the double integral or something. And same thing for marginals. If you want to calculate your marginal, you need the marginal PMF or PDF. You do the calculation. And then you also need to know, like, yeah, basically using the chain rule, how to move between joint things and marginals and so on. And it's just like rearrange this formula. Like if you have this object and you have this object, you can like calculate this, or you can just marginalize by taking the sum over all the y's. And we've seen these kind of equations. So I guess get familiar with that stuff. And on your formula sheet, yeah, there's kind of equations for, we'll get to expected values in a second. So an important thing is this property of independence, which will help you do a lot of calculations. And this is where you need to know. If you have a random variable and you're told it's independent, then that means that its corresponding PMF or PDF, its joint PMF or PDF can be decomposed as this product. And you can imagine this makes all your calculations way easier. Because now you can like separate sums into separate sums of things and so on. Yeah, so if you ever needed like the probability of this multivariate thing and it's independent, then you can break it up into this thing and calculate each one of those kind of one by one. And you should have seen this in some of the assignments. So if you see independence in a question, it's very likely it's going to help you by decomposing it in this way, or we'll see in expectations, you might not even need to do this step because something else will happen. Okay, so yeah. We'll come back to the independence thing for expectations, I think. But if a function, yeah, and then the other thing to know is functions of random variables are random variables. Okay, and then everything is kind of the same story. So if you have a random variable and its outcome space is x, and you have a function that maps x to y, well, then that function is a random variable. Sometimes it'll be called something like y. And its corresponding outcome space is the range of the function, which makes complete sense because it's just the values that the corresponding function can take. And so one example of a function of random variables we've seen is, for instance, the sample mean, which is you take the sum of n random samples of like a coin flip and you divide by n. This is also the same looking thing as the empirical risk. It was the sum of n losses divided by n. And those losses were calculated based on a predictor and each feature label pair in your data set. Okay, And yeah, so then there's expectation and variance. They're all on your formula sheet. There's a bunch of like equations, but the story of all of them is almost the same, which is the expected value of any object is just going to be kind of, you take all the values of that random variable. So, okay, the expected value takes in as input a random variable. And what it does is it's going to sum or integrate over all values times the corresponding probability. So it's like this weighted sum. And then the things that differ is just literally what are you weighting it by. So in this case, well, these are, turn out, here you weighted by the probability of x. Here you also rate weighted by the probability of x. If you have a function of a multivariate thing, you will weight it by the multivariate, or the, what's it called, the joint PMF PDF. For the conditional version, the weighting is by the conditional PMF or PDF. And then there's this variance, which has like another simple formula on your formula sheet, which I seem to never remember, but it's one of these. It's either this guy squared minus this or the other way around. I don't remember which one it is. So you should take this with a grain of salt. It's one of these directions. If someone can remind me, that would be, if it's wrong, tell me in the next few minutes. Okay, good. I mean, we could, yeah, if you expand it out, you should get this, but okay. So that you have this formula. This will help calculate variance a lot of the time, because like in questions, you might be asked, like, what's the expected value of something? You calculate that. And then in the next question, you know, they're going to ask you maybe about the variance. And like the hint is that since you've already calculated the expected value, you can then square it and get one of the terms. And then you're just left with calculating one more expected value. And that's not too hard. You just square the internal thing and you're done. But if you want to like explicitly write this out, that's going to take some time. Yeah. So you can definitely expect to calculate the variance at least once, potentially using this trick. All right, then there's supervised learning, which is what we were actually here to learn about. And yeah, you need to understand that the data set, importantly, is a bunch of independent and identically distributed samples. So this is the identically distributed part. They all come from the same feature label distribution, and they're all independent, meaning the properties for independence above hold. And that allows us to use like the sample mean estimate as being like a good idea and things like this. And so, yeah, and then we've talked about the learner. It's this mapping from data sets to functions. Yeah, you should understand what that thing is. There's a predictor, loss. Okay, like a loss function takes in two labels and compares them and gives you a number. It's a measurement of how close are two labels. That's the rough idea. And that's why you have one label, so an element of one label set, and then the element of the same label set. You compare them in some way. For instance, you take their difference and square it, and you output a number. How many pages do I? Okay, let's move a little bit faster. And yeah, so that's then the expected loss gives you kind of like a weighted sum of losses based on the probability of getting the XY pairs. And your objective is to minimize the expected loss in expectation over data sets. So this is like, you want to weight the expected loss, which is the risk, by the corresponding probability of getting different data sets. And that was to deal with the fact that indeed this data set is random and it might change, and then your prediction might change. So you want to talk about how well do you do as data sets change as well. That's your final kind of objective. Okay. Then there's two ways to break up supervised learning problems into regression or classification. And you will definitely be asked at least one question being like, hey, I have these kind of labels. There's some notion of order, which you're going to have to kind of deduce based on the question. If there is order, such as if you're talking about like the real line or the intervals, like predicting house prices, well, then you're going to have a regression problem. And losses you might want to use are the squared or like the absolute loss. And classification is when there's no notion of order in the labels. So you can't really compare them, one being closer to the other. So things like if you have cats or dogs, these are called categorical kind of labels. And there you can't really compare them. And there you'll use like the 0-1 loss is all we've learned about so far. And then this like learner, which you have heard about a lot now, is ERM, stands for empirical risk minimization, as 2 steps. You need to estimate the risk with the empirical risk, and then you optimize. So roughly knowing this procedure is important. Okay, and then all that's left is estimation and a little bit of optimization. So estimation, really the thing you need to know is you have random variables, they have some distribution P. You want to know some number that describes some property about it. An example of such a number is the expectation. And you have data, and somehow you want to estimate this number using data. And really all we've learned about is that if you want to estimate the expected value, one way to do this is to use the sample mean, which is you have n random variables coming from the same distribution, you sum them up and you divide by how many there is. And the beautiful thing about this is that this sample mean estimate satisfies two properties. First of all, its expected value is equal to the expected value of any one of the random variables. That's great. And that its variance decreases as 1 over n. So the more samples you have, the less it's varying from its true expected value. And so, yeah. Okay. And this only holds, these calculations, if you do indeed have independence and identically distributed n samples. All right, and then finally, optimization. You need to know this notation because you'll definitely be asked, like, calculate this. So you need to know what min is, argmin, and some of these properties. I think this might be on the formula sheet. I don't remember, but you should probably know this. And you need to know like this thing. So if you're tasked with like a discrete optimization problem, which means your domain is discrete, then literally just plug in, like maybe it's like the domain's like 4 points, just plug them all into your function and then check which one's the smallest, and that's the minimum. But if things are continuous, then we're going to use derivatives. And you can actually find the true minimum if two properties kind of hold, which is if it's convex and if it's twice differentiable. Yeah, so if you have a convex function and it's twice differentiable, then you're going to be able to take the derivative and set it to 0 to find the minimum. And that's the case where your domain is all the real numbers. Otherwise, you should check the endpoints. So that's if your domain is smaller. And then there's like a definition of twice differentiable. It's obvious. You take the derivative twice, and if it exists, you're good. If you have an absolute value, you're going to run into trouble. Convex means the second derivative is greater than 0. You're also going to need to remember this property. And roughly speaking, you can like kind of draw these functions, and if they're bowl-shaped, they're convex. And then the final thing, yeah, this is the last thing, which is in this multidimensional case, I will tell you when things are convex, so you're never going to have to calculate that yourself because it's more complicated. And when I tell you it is convex, then you can just go ahead to find the minimum. You can go ahead and just take the partial derivative of your function for each dimension and set it to 0, just like we did in today's class. And that will give you the minimizer, W star. And if you plug in the minimizer into your function, you get the minimum of the function. And that's all we kind of covered up to the midterm, though you'll be asked on. Okay, so I end there. Good luck on the midterm. And have a good weekend, everyone.